In this video, I'm going to be going through a past trial question that can be solved using the three-force method. So there's a picture that looks something like this. They don't show it as a curvy reaction, but they've labelled these points as this is point A and this is point B. They've told us that there's a 100 Newton force being applied at the top of the bracket, and that there's two reactions. There's a cable that's holding the bracket down, and there's reaction here. Now, what we can start to say intuitively is that if I'm pushing this bracket here, in order for this to balance, just like if it was a seesaw, if I'm pushing this way, well, there's going to have to be a force pulling that cable down. So that makes sense to say if I'm pushing this way, there's going to have to be a force going down. Also, if I have some amount of left force this way, there's going to have to be a force pushing to the right to balance that as well. Yeah? So we know in this case that this is going to have to be going up and to the right. Okay, so I'm going to draw this as a simplified version of the diagram. I'm going to draw my 100 newtons at 30 degrees. And I've got my reaction B. And unfortunately I don't know the angle of reaction A. But we're going to use the three-force method to solve that. If we didn't want to do this, what we could do instead is we could use, we could find the moments in each side and solve that. And that's how most people would solve this question. They would solve it by taking the moments. But what we're going to do is we're going to look and see how we can solve this instead using the three-force method. So what we're going to do is we're going to find, first of all, we're going to say, does the three-force rule apply? Well, I've already said that it does. But let's think about what does it need to be for the three-force rule to apply? It needs to have how many forces? Three. And they need to do what? They need to meet. Yeah, they need to be concurrent forces. What that means is these two forces that we have, do they meet? Yes. They meet somewhere in space. If they meet somewhere in space, if they're concurrent, then that means that all three forces must be concurrent, because that's just the rule of forces. If they're in equilibrium, which everything we do is going to be in equilibrium. So what I'm going to do is I'm going to extend these lines so I can find this point of concurrency. So step 2, I draw the location where they meet to find the point of concurrency. Step 3, I then draw the green line from the force that's unknown, right? This force here is unknown. I don't know the angle or its value, its magnitude. And I know that it's going to go to the point of concurrency, and I draw a line there. I measure this angle, and I can call that theta. Now, I then need to do my force polygon, my vector diagram. In this case, it's a vector triangle. What do I know? Well, I usually like to start with the vertical force, so I said we've got RB, the reaction at B, going down. I've got this force here at 30 degrees, and I've been told that that's 100 newtons. Okay, that's a pretty good start. Just checking, do our forces go tip to tail? Have I drawn them tip to tail? Well, which way is this 100 Newton force going? Down. Okay, so that means that the sharp part of the arrow is touching the feather part of the arrow. Yeah? And so we're missing, what force are we missing? Well, if I draw this at the actual size, if I draw this at a scale, and I'm going to set for my scale, I'm going to say that 200 millimeters equals 100 newtons. That's what I'm going to draw as my scale. So I'm going to write that here. For me, my scale is 200 millimeters equals 100 newtons. Now, let's check that I've got 100. Yeah, okay. So that's my scale. I don't know how big this one is yet, but I know this one size. But with a triangle, once I know this one size, I can measure this angle. Now, I would have to actually look at the diagram to see that angle properly, because I've been drawing this on the board. Does anyone here have a protractor? Okay, who's drawing the concurrent forces? bear with me. You might want to hit the skip button if you're watching this on the YouTube. Okay, so I've got my pen. Anyone got a red pen?
Yeah.
Pass me a red pen. And you've got a green pen. We're doing it live, YouTube. We're doing it live. I'm guessing I'm off camera. I'm just talking, keeping the viewers engaged. Oh, I'm going to say this angle is really close to 60 degrees. I'm going to say it's 61.5 degrees. Theta equals 61.5 degrees. There you go, YouTube. There's your payoff. So you can see I've drawn my red lines to find I didn't label my point of concurrency, but you guys know where it is. It's up the top here. And then I've drawn my green line, and then I've marked my angle. And I've measured my angle with my protractor. Pass that around. Okay. Now that I know my angle is 61 degrees, what I can do is I can use that angle to draw my diagram. Now I'm going to have to set my protractor upside down for that to work. Okay. And I've got a little bit left over. I drew a little bit too much originally, so I'm going to clean that up and remove that. Okay, which way is this arrow going to go? Is it going to be going up or down? Now, that matches with our prediction earlier. We said that it'd have to be going up and to the right earlier. Now, what we can do now is we can measure it. We can just take the ruler out and we can measure. Okay, so this line here is 210 millimeters. 210 millimeters is going to equal how many newtons?
105. No. Yes.
You got it, 105 newtons. Okay, this one here, might have to do this in two parts. 200. 3, 5, 4. Oh wait, I should have written that in green. 3, 5, 4 millimeters. So that's going to be
127.
It's going to be
No,
170. 177? Yeah, that sounds about right. Okay, that's my answer that I've got so far. But that's using the graphical method. No one likes to do the graphical method. They can accept that they have to get the protractor out. They can accept that, but beyond that, let's say that most people instead they want to use the sine rule. Everyone loves that sine rule. Me, I never use the sine rule. I have a protractor. Okay. So I said this here was 30 plus 90. So what's another name for that angle? 30 plus 90 is? 120. Okay, down here, I found this angle. I said that theta equals 61.5 degrees. That is unusually precise for me, but okay. 61.5 degrees. What's this value going to be? 28.5? That sound right? Yeah? Okay. And then what's this value going to be then? $180 minus 120 minus 28.5 equals 31.5. How did I calculate that? On a calculator, but what was the process I used?
Subtraction.
The angle sum of a triangle is 180. That was the concept I used. Okay. Now, if I'm going to say that I want to, let's say, which one do we want to find? Do we want to find reaction A?
Yeah.
So this is reaction A. and this is, oh yeah, 100 newtons. This is reaction B. Okay, so if I want to find reaction A is going to equal or rather we say reaction A over sine 120 equals 100 newtons divided by sine 28.5. So that means reaction A, or Ra, equals 100 sine 120 divided by sine 28.5. So Ra equals 100 divided by, 100 sine 120 divided by sine 28.5 equals 181.49. So we're going to call that 181. Okay, what was my answer? 177. Pretty close. Pretty close. Right? Well and truly within 10%. Now, again, I drew this with this thing. Right? So, I will say it's harder to draw on a whiteboard than it is to draw on paper. If we were to do this one, if we were to find RB is going to equal RB over sine 31.5 degrees equals 100 divided by sine 28.5. So therefore RB equals 100 sine 31.5 degrees divided by sine 28.5 equals 100 sine 31.5 divided by sine 28.5 equals 109. Newtons. It's important I actually include the angles for vectors.
Oh yeah.
Oh yeah. Okay. Again, if we compare our answer, we're off by a pretty small margin. We're more than happy with that graphical solution. So, to recap, there are four steps to using this method. First of all, we have to check that the method applies. There needs to be three forces, and the two forces we know the angles of have to be concurrent. They have to meet. Okay, once we've determined that they meet, we use the red line to find the point of concurrency. Once we find the point of concurrency, we can then use the green line to find the angle of the unknown the unknown force. Once we find the angle of the unknown force, we can then either solve it graphically. You saw I just drew a graph. Yeah, I just drew it up with a piece of paper, and in my case, whiteboard markers and a pen, and a protractor. Or, once you know the angles, you can use this. What do you need to be able to do to use this method? You're going to need a protractor so that you can find the angle. Now, a little tip that I had students say, what if you didn't bring a protractor into the exam? Do you know what I'd do? I would draw it close and I'd take a guess at the angle. I would say, let's call the angle 60. Right? And I would say, you know what, I would maybe, if it was me and it was for a trial paper, I'd say I didn't bring a protractor, but I guessed that the angle is probably about 65 degrees. And as long as you made a reasonable point, you've shown me that you know how to do it. The HSE, I probably wouldn't give that if someone just made up an angle. Oh well, I'd call the senior marker, and the senior marker would tell me what to do. But I will say that they're generally pretty lenient. They want to see process. They want to see that you know things, not whether or not you brought a protractor. Okay, hopefully that helps clear up the three-force method.